Halloran from D-RisQ. Colin's been involved in safety critical systems one way or another for a good long time, let's say, Colin. And recently he set up this company called D-RisQ, whose main goal is to develop tools for the development of safety critical systems, but they do various other things as well, including quite a bit of research and participation in the TAS node, of course. And he's going to tell us a bit today about well, DO178C, which is the avionics software standard, safety critical software standard, and the corresponding formal methods advice or standard, which I can't remember the name of, but it's got 333 at the end, I believe.
Got threes there in various places.
Yeah. Okay. So anyway, I'll hand over to Colin. Thanks, Colin.
Right. Hopefully you should be able to see my presentation with banner.
Absolutely, we can see it.
Good. So I say we're going to do a focus on costs and certification. So I'm not going to get into arguments about using formal methods gives you perfect software or really good software. I believe it is, but I don't think there's an empirical way to actually demonstrate that. So the empirical aspects we can concentrate on are the cost of developing such systems and software. And that's what today is about. And I'll be unashamedly promoting the tools that we've been developing in order to achieve the sort of certification evidence that I've been talking about at a significantly reduced cost. So for system software certification, of course, you start off with your system requirements, and then parts of those are those allocated to software. So you have your high-level software requirements, your software design, which will be an architecture and low-level requirements. And low-level requirements are those in which you directly code, the source code, of course, and compile to executable object code on a processor. And there's an obligation to show that your high-level software requirements meet those system requirements that are allocated to software. And similarly, there's a satisfaction you need to show that the design meets the requirements, the source code meets the design, and the executable object code ultimately meets the source code all the way up to high-level software requirements. And I'll go into a little bit more detail with some diagrams I will show. Now, I'll be talking about D-0178C, referring to it, but I won't be going into any detail. That is a 3-day course, which we haven't got time for, and you would probably need to pay for. So I'll be touching on these aspects. I've sent a copy of these slides, PDF, to Andrew and his colleagues, so they can be distributed. And of course, I'm presenting this as in the way that D-0178 does, and to like a waterfall, but it's just as applicable to other types of development, such as Agile. And as the blue lines indicate, you need to show that the object code satisfies software design and the high-level software requirements. So it's not just about object code to get source code, it's all the way up to software requirements. And here I show that you can start with your requirements, you throw down your requirements. The first ones you're going to do, you think of, go ahead with design in an agile sort of way, code, do some testing or verification, integrate it, and then you do an iteration, go around again. So the need for certification evidence or verification objectives to be satisfied doesn't imply that you have to use waterfall. It's just as applicable to agile. And of course, the point of this is to produce evidence for a safety case, or certification evidence that you can present to a certifier in the aerospace sector. And it's important to point out the development cost. Well, that's the easy bit, as it were. It's 20 to 50%, but the certification, the verification cost can be 50 to 80%. So 80% when it's level A software, the most safety critical level of software in the aerospace terms. The cost is driven by the certification, the verification, that evidence that you need to produce. So how are we going about doing this? Well, we're producing a number of tools. We have Capture. Let me just move this slightly so I can see the other screen. Capture, which is a tool for, guess what, capturing high-level software requirements. ModelWorks, which then allows you to be able to check the architecture and the low-level requirements, i.e. the design, against the software requirements. Clause, which checks against the source code against the software design. And Fever, which is under development, and I'm not going to really say anything about today, which is looking at executable object code and verifying that against source code. And all I will say about it is that it's basically the sort of techniques that we use for cell4 verification. So we're using the decompilation, verified decompilation tool, Magnus Mirin developed, and Anthony Fox's L3 tool for expressing semantics of instructions, various instruction set architectures, and that's very much ongoing work, which we hope we'll have a prototype for next year, but don't hold your breath. And stand by. So this will be familiar to Alice and Andrew, who are on the call, looking at system requirements, and I'll talk a little bit about that later. So as I say, I'm talking about RTCA D178C, or in Eurospeak, it's EuroK ED12C, and associated documents. And although we do kind of talk about it as a standard, it's not actually a standard, but it's a de facto standard. It's sort of, if you're not using D178C for your verification objectives, you've got to give a pretty damn good convincing argument for why you aren't. And it's probably easier and more cost effective to actually follow that. So what are these verification objectives I'm talking about? Well, they break down into these in the same way I was talking about the kind of waterfall. Your system requirements, again, allocated software, high-level software requirements, your software architecture and your low-level requirements, source code and executable logic code. And these references are, these annotations are references into D178C, where you can look up in the appendix about what is required for that. But I'll go in next a little bit more detail. So you need compliance and traceability from the high-level software requirements. Those system requirements are allocated to software, and there are aspects in terms of accuracy, consistency, verifiability, conformance, algorithm accuracy. So these are verification objectives which are summarized in a table, at the back of D178C, but this is not a tick box thing. This is something which you look at in terms of summary, and they reference paragraphs, specific paragraphs within D178C, which you need to look at and interpret and use and work with certifiers in order to be able to provide the evidence, necessary evidence. There are similarly summary tables of verification objectives, and they kind of here the high level headlines for those. So there's architecture compatibility, compliance and traceability. Again, you can see it's a common thing. Consistency, hardware compatibility will start to come in. Again, verifiability and conformance, and then necessarily partition integrity, where you have different aspects where you may have lesser critical software or non-critical software. Make sure it's partitioned from critical software. And there are further objectives here. And then as you go down, again, the same sort of thing that takes place in source code against the architecture and low-level requirements and the executable logic code. But here's the thing, you still need to show, as well as compatibility to target, that that you can verify the executable object code get your low-level requirements and your high-level software requirements. So ultimately, you have to go always back to the high-level software requirements. So if you're doing testing, you're doing testing against high-level software requirements. Now, this is the aspects which are to do with how you compose all these things to get this evidence. And these last part are really about aspects of how do you verify the verification approach, because D-R178C is very much a testing approach. So you come with these decision coverage, statement coverage, modified condition and decision coverage, how much testing you need to do in order to be able to show that you've done enough testing, that you've met the high level requirements. And then there are some additional things like untraceable object code. So is there any object code that's present there, but doesn't satisfy any high level software requirements? So why is it there? You have to account for every piece of code, which has the so interesting issues when you talk about defensive programming. So I'd say I can give it away in the calling notice for this, but an observation of this is that, well, certifiers need to understand high-level software requirements and that they're sufficient for safety. So following D-R178C doesn't mean it's safe. It just means that you've shown the verification evidence that the high-level software requirements that you've articulated have been met by the object code, or insufficient evidence to assure that. Doesn't mean that they're safe. So there's a wider context about when you set the allocation of level of software and what it means for system safety. So it's an important aspect in terms of the high-level software requirements need to be understandable by a human being in order to assure themselves that whatever processes they may follow as well or review, it gives safety for safety critical software. Then, if the requirements cannot be articulated, then what do you verify against? And I believe this is a challenge for machine learning if it's to replace decision making in safety critical applications. So there's don't misunderstand me. There's a role for machine learning, but it's understanding where it can be usefully used or cost effectively used, I think is important. And if you can articulate precise requirements, then why not implement without the use of AI with its associated risk and cost? Now, obviously, that doesn't preclude it from a research topic about how you might do this, but in engineering sense, it's why do that? It's certainly not going to be something which I think is going to be done purely in terms of AI. Now, there is a halfway house compromise that you can make in terms of maybe using the best aspects of both, where you have precisely defined high-level software requirements, and then you implement a safety cage around an AI. So AI might be able to do things, achieve the objectives that you want in a more smoother way, more efficient, whatever. But when it comes to the safety boundary, the envelope, if you like, of the safe behavior, then you have something which monitors and can intervene in a safe way. And that's something that we've pursued for collision avoidance, for aerospace, for autonomous air system, maritime, surface and below water, and using our tools. So eating our own dog food, if you pardon the expression. So D0333, which is the formal methods aspect version of D0178C, it looks very much, and it should do, very much the same as what I showed for D0178C, because it appeals directly to text within D0178C. So it's not doing anything different except for the testing approach. So it's replacing testing by formal verification. So you still have the same sort of things about procedures are correct, but then you'll notice that there are these additional objectives which D0333 introduces, which are to do with things like the are using the most appropriate form methods. Justify that. You can't just say, which I've seen in the past, I'm just using this static analysis technique, so that must be okay. There's a whole aspect in terms of justifying the use of the formal verification and the soundness of it and the qualification evidence, although that's largely covered in a separate DO330, I think, in terms of tools, which also applies to testing. So the other thing to draw here is standards and verification. So we're quite well aware of coding standards. So, for example, Spark, if you like, is a coding standard that's embodied by and enforced by a tool. There are similarly coding standards which are more informal, and the ones which aren't so useful are things like about indents and how you might lay out the code. MISRA is somewhere between the two in terms of C or C++. So we're familiar with coding standards and how they can be policed. To a certain extent, we're also with design standards, although maybe not quite so much. So use of UML, SysML, even Simulink and Stateflow. There's always a constant pressure to add more bells and whistles to these things to make the life of the software engineer to get to code as fast as possible and to make it as painless as possible. Now, as I say in a minute, that's not necessarily the whole story, especially when you talk about safety critical software. What less enforced are the requirement standards. So the requirement standards that do exist, they tend to be talking about the use of the word should or shall or will or how you might phrase it in informal language, which is a bit like the code layout standard you might have for some coding standards. And what we want to be able to do is to take that further to satisfy what DL178C actually says and other standards implicitly do. So it's used these standards to develop artifacts in part of software development, but so that they can be verified. And that's quite often missed, especially in things like requirements. You can write requirements, it shall be black or red paint be used. But little thought is given to, and how do you verify this? And you come to the end of a project, you produce a software, it's going to go to the certifier. They independent people come in to do these checks of what has been produced. They do these traceability all the way up to and they say, well, how do you verify such a requirement? And it's surprisingly how often some of these requirements are just not verifiable, especially when you have a negative requirements are, it shall never do this. That's a bit of a challenge. So there's a cost issue associated with that. And I say it's like this, making it easy to develop in terms of bells and whistles, all sort of support you can have, and getting to code as fast as possible. The tension against that, as opposed to being easy to verify. And as I'll show, it's the verification costs, which drives the cost and time in terms of projects. So as it says at the bottom, numerous projects fail due to lack of emphasis on certification. Indeed, there's one case that we know we're involved, not involved in, but we're from the outside, where a company was redeveloping a piece of software that they'd already produced and had certified and so forth onto a new piece of hardware and maybe some of the protocols. So it's updating it basically. It wasn't doing anything new; it was just updating it. And a budget of $3 million was set for that, and that escalated to $25 million. And that's all due to the fact that the certification hadn't properly been accommodated. So there you are, there be dragons. So this is a kind of typical cost profile for level A, i.e. the highest level of safety criticality in aerospace. Which we've had validated. It is these are indicative figures, but they're typical of these sort of things. So you start off with requirements. That's the it's easy to write requirements, isn't it? But it's these verification costs which drive the increase in cost in terms of the software development, and especially at the end, when you find that's typically when you find that your requirements weren't right, or you've implemented the requirements in the wrong way. And I said this cost profile is independently validated by York metrics. So I'll be coming back to that. Now I'm going to unashamedly promote the tools that we're developing. So starting with software requirements, we're using the tool called Capture. So being clear. So if only we got the requirements right at the beginning. If only we got the right requirements at the beginning. However you phrase it, whatever the aspect, a lot of problems can be traced back to requirements, although occasionally there are in terms of coding errors. Requirements issues, well, you have ambiguity, duplication requirements, consistency requirements, undefined conditions, etc. It's not an exhaustive list, but I'm well aware of the sort of issues that come up in requirements definition. So you have your human who's writing a high-level software requirements using Capture. Using Capture enables this table about the verification objectives to be addressed, or in this part of the agile path. And this is what Capture looks like in a snapshot. So we've got ways of recording assumptions, data dictionary, definitions and requirements, filters, individual record viewing, trace, reference and comment features are important. So traceability up to the system requirements and down to aspects of the design. That is a tedious thing which auditors come in and look at. So making that easy is a good way of passing your audit. You have attributes of it about issues where it's a derived requirement and safety requirements, security requirements, how you might verify it. Of course, we've got ModelWorks here, which I'll talk about, but it could be by review or by test. It doesn't have to be by ModelWorks. And then your project requirements, which are indexed, grouping of requirements, and the verification method. And this is what a template looks like for Capture, which is essentially structured English, which we've evolved through a number of years through direct application development of such software, which needs to be sure, whether it's in automotive, aerospace, maritime. So common things keep coming up, and this is basically a distillation of what we believe are useful templates for such requirements, and they seem to work. And we're not claiming that they're complete. They're the sort of things which can evolve and we can add to it, but it seems to work in terms of our industrial users. So here are the table that the verification objectives are relevant to Capture, and focusing on two. The high-level requirements are verifiable, and they're verifiable because due to provision of formal semantics that underlies Capture in terms of the structured English, and that they conform to standards well because you're using a tool that polices what you can and can't do. That's implicit. There are other things which it can't do at the moment. So about how do you show that the high-level software requirements satisfy the system requirements for allocated software. That's a manual review at present, but I'll come back to that. Then there are those which are partially met, where Capture helps but doesn't provide all the information. So requirements, that's very useful to get something like that, even if you don't use any other verification tools and continue by the sort of normal route you might do with verification objectives based on test. What we would like to do is to go the next step, which is introduce automation in terms of formal verification of the design, which is architecture and low-level requirements against high-level software requirements. So this is an overview of the ModelWorks process. So we've got automatic parts, manual parts, and mixture of the two. So here you have your capture requirement. Here you have your design. Now, remember we were talking about standards for design as well as for requirements and coding. This is where we do use a model advisor, which is a tool provided by the MathWorks to go through Simulink and Stateflow. So remember, I was saying about all sort of bells and whistles, all sorts of things which system designers, and you like to do all sorts of simulations and try all sorts of fancy things. Well, that's great, but there's implications, say, for verification. How do you verify some of these things, or the cost of doing that, or the difficulty? I mean, we don't cater for everything, partly because we just haven't been able to do that yet. So we're starting with a core, a subset of what can be verified, and our intention is to build that up like an onion to try and accommodate more and more. But there's still an aspect of discipline that is needed in order to be able, in the same way Spark does in the programming language level. So as I said, capture requirements have a formal expression, formal semantics. So you have a formal requirement which underlies the informal structured English. Similarly, for the design, we've blessed it with a semantics, which we then have a obligation to do validation to make sure that our semantic description keeps pace with what the MathWorks are doing with Simulink and Stateflow, because they change it every 6 months. And you link these two together in terms of the entities that our objects you're talking about through an entity dictionary. Feed those into the ModelWorks tool, and either you get proven, tick, off to coding you go, or more likely, oh, you get a counterexample. And that counterexample then can be fed into the Simulink animator in order to be able to explain what the problem is in the problem space of the designer who's using Simulink and Stateflow. So it gives it in a explainable, understandable way. And then that feeds back to, well, either the requirement wasn't quite right or the design isn't quite right. We don't know. Just there's a mismatch between the two. So that's where ModelWorks fits with capture, and it addresses some of the verification objectives of FMA4. So again, remember there's more green now, and here we have the verifiable and conform to standards focus on, and some help with low-level requirements complying with high-level requirements. And that help, and that where you have escapes is where you have derived requirements, and there are interesting issues of what counts as a derived requirement, or are they just requirements you forgot about and only discovered later on. So, but that's kind of more a philosophical thing. And those are 7 objectives of the first part of the table, and there are further 8 to 13. And this is to do with architecture. So the design is architecture plus low-level requirements, remember. And again, it's about, is it verifiable? Does it conform to standards? Cost savings. So I remember I was saying about what I hang my hat on is what you can measure is the time it takes and how much it costs. So this is something we did back 5 years ago, which was part fed into the electric vehicle for Land Rover. And they were developing the safety requirements and various aspects of the system to manage that to do with charging. So one requirement might be that it's impossible to start the car and drive away while it's still attached to the electric cable, else you have some interesting consequences. And what you can see in this graph are the conventional methods that they were using in order to generate this evidence, this time for ISO's 26262 or some number like that. I always forget. the use of the MathWorks products, the Simulink Design Verifier, and the use of ModelWorks. Now, this was done in the context back in 2017, before we had the capture tool, before we had developed it. All we had was a language which you need to manually express and feed into ModelWorks. So there was a lot of manual effort associated with that, which has now gone away. So these figures in green are actually worse than they are now. Now, eagle-eyed among you might notice that where's the green bar here? That's because the metrication program ran out of time funding at that point. So we're never able to feed the figures that we had for that in for the comparison. And the other aspect is we've got the same subsystem as part of the overall system, which has been done independently by two different companies. Now, one was Johnson Matthey, and the other was Ricardo, I believe. Yes. And not only that, but they had independent, so they weren't communicating, they were geographically separated, and they in teams who were working on these different parts were different and independent as well. So that was part of the experimental setup. And so this was quite nice, being able to show that, that they were broadly in line. So it's not definitive proof, but it's kind of nice indicative evidence that the measurement framework was producing something useful. And the other thing to note is that in these particular systems, subsystems, the use of the Simulink Design Verifier was actually more costly, took more time, really, strictly, effort in hours, to use than the conventional methods. And I believe that the reason for that is that if you use Simulink Design Verifier, it's rather like doing assertions in the code where you have Hoare triples, where precondition, the statement, and the postcondition. In this case, it's like a precondition, the blocks or the subsystem, and the postcondition. So you have to, which is very good because it gives you a very thorough review of the system and what it's doing by planting those assertions, and you've got an implacable reviewer, which is the Simulink Design Verifier tool, which won't let you say yes, it's verified until it's checked the postcondition in the normal sort of way you might do for a Hoare triple. But there's a lot of manual effort associated with that. And then the other thing is that these is probably the better one to use. The use of ModelWorks over the conventional approach gave you something like 80% savings. There's always going to be some sort of cost to using these things in the first place, even with automated verification. And as I say, these things can be reduced by the use of capture nowadays. So going back to these verification objectives, we can look at this particular part, which is to do the use of capture and ModelWorks. Put it up there, look in terms of the cost. So this will be kind of typical cost profile I showed before. And for large enough systems, we can show that the trials that we have done, they can get in around 80% direct savings in this area. Now, what does that mean in terms of the whole life cycle? It doesn't mean 80% savings for the whole of that, but it does reduce the costs by up to about 25%, just when you're looking at design verification against requirements. But inevitably, there are indirect savings because errors that would have manifested themselves right at the end have been eliminated now. So it's reasonable to claim there's about 33% saving just with those two tools and that activity up front. But we don't just want to give you that. So we've got the tool clause, which is looking at the aspect in terms of source code against design. And we're due to have say a beta version for Simulink and Stateflow in December. We already have a version just for Simulink, which is extant. The overview of the clause process is very similar to the in sense the ModelWorks, in that we use a commercial off-the-shelf autocoder, in this case target link from DSpace, The Simulink generates the code automatically. That's forward development, so that's completely automatic. And then we have a underlying semantics for Simulink, which we bless and therefore have an obligation to validate. And then using Theorem Prover, in this case Proof Power, which you can build tools on top of. In a particular case, it's a compliance notation, a compliance tool, which we're using and generating verification conditions in the same way basis of a Hoare triple. You go then, proven, great, off to compilation, or it fails. It shows the where the error is in the code, and actually with the simplification of the verification conditions, rather than just leaving it as a big blob of mathematical symbols, it simplifies as much as possible. And quite often you can see it suggests the answer, what it should be, how the assignment has gone wrong. It's should be x plus 1 or x times y or something like that, rather than what is actually in the code. I can't say that's all the will happen all the time, but it's has happened whenever I've used it. And it's it builds on work we did in Clause for Ada, which did a similar sort of thing. And of course, if you get a failure, well, you can correct the code, but what you should really do is go back to the autocoder and fix that. Make sure that you eliminate that systematic error. And so December, we should have Stateflow integrated in with Clause as well.
So, Colin,
yep, go ahead.
How often do you find errors in the autocoder?
Sorry, I didn't quite catch that. How often?
How often do you find errors in the autocoder?
Oh, very few times. So I'd expect the autocoder to be 99% plus correct in terms of the code it generates. But that's not the point. It's to be able to demonstrate that it has produced correct code in the particular instance. So it's good news, because you get automatic generation code, which generally you can rely upon, and occasionally you might get an error. I think in terms of the number of years, a handful of errors in an autocoder. But again, it's about the if you are following testing approach of D-RisQ, you still have to do testing to show that the source code satisfied the design. So you can't get away from it in terms of verification objectives in D-017HC, D-0333, or indeed any of the other standards.
Okay, great, thank you.
No problem. Right. So that's where clause fits. Oh, and it addresses the objectives in table FMA5. Still, some of these are not, you can't support because they're things like parameter data item files correct complete. That's to be done separately. Output of integration process complete and correct. Again, it's kind of review analysis. So it's not a silver bullet. There's still these things that have to be done manually, but it's reduced the effort quite considerably, and it has helped in this area. And again, I focus on the verifiable, and it conforms to standards, because you are using a subset of C, which we call C flat, which has a formal semantics, and it checks that you your code that you generate conforms to that standard, which is fairly expressive and generous. I would say it's a kind of subset of the MISRA-C, because the MISRA-C does go into constraints about names that you use and so forth, and indeed layout. And indeed, for non-application software, so we're talking about might be a control system or whatever. So while we're focused on the application software, you've still got things like drivers, libraries, real-time operating systems that you have to consider. And the clause compliance checker, which I talked about, which is built on top of Proof Power, as that's available to check compliance with C-flat coding standard. Indeed, we're working with a client who's developing some of their software applications. So use Simulink and Stateflow, and other where they're writing it manually, and we can still use the compliance checker to show that it's complies with this predictable, verifiable subset, which you could take to the next level and verify against a specification, but you have to construct that specification separately, and you don't get it automatically as you do in this approach through ModelWorks, Simulink and Stateflow. So looking back to the standards again, we've got requirement standards, design standards, and the KISS coding standards, C flat I talked about. So the artifact created is for requirement standards, software requirements. The language is English, structured English, so stylized English. And the artifact is created by a person, checked by capture intrinsically. Software design, again, Simulink and Stateflow, which a person does, so it's creative, but it's again checked by ModelWorks against the capture, and Model Advisor checks whether it's in the subset, which is we can support. Source code C, autocoder, so there's no human being involved there, and use the clause tool and the compliance tool to check that the code generated is in this predictable subset. The coverage. So I skipped over Fever, as I said I would, but when you put all these tools together, compose them together, which you don't have to, you can use these things individually, but the real benefit comes when you chain them together and get the table FMA7 objectives, which is down at the executor logic code, linking back to the high-level software requirements under D-RisQ. So here you get greens mostly, apart from here where it's the verification coverage of software structure is achieved. That's this aspect of dead code I was talking about, trying to identify that. So the Fever tool that we're developing can identify semantically impossible paths, but that isn't necessarily dead code. Dead code would be semantically impossible to execute, but there are so you know what I'm talking about. Now, if you can compose all those tools together in the chain, generate the sort of evidence that you need for verification objectives, then our projections are that if you add that in, you get something like 60% saving over the whole life cycle. Now that becomes a very attractive proposition. So rather than spending $20 million, you can reduce it to between $5 and $10 million. Well, that's good money in anyone's language. And by appealing to all these aspects of D-RisQ, including this in terms of the additional objectives of justifying what we're doing. What I haven't talked about, which is a support of this, is tool qualification. So how do you know that the clause tool or ModelWorks does what it claims to do? That's separately covered under D-RisQ, I think. Or something 3.3 something, and that's again something we need to go to the certifier to present the qualification evidence. Right, so we're talking about from high-level software requirements all the way down to code. This is something we just started this year and due to complete next April. So this is a NATEP, basically funded out of the Aerospace Technology Institute funding, delayed from last year. It's a one-year program, and we're working with the University of Glasgow, and Alice is on the call here. Heriot-Watt University, Andrew Ireland is here as well, and they're looking at probabilistic requirements of exploitation of PRISM. So when you start talking about this system level, you're starting to touch the real world, which isn't like software, has a probability associated with it. So it's exploring the use of how we can leverage PRISM in order to accommodate that. It's more of an investigation in terms of what's the art of the possible. It definitely won't do everything, but it'll be again indicative of the sort of things that are possible, and link it to capture. So how capture can seeing this. So it'll look at the FMA3 objectives, look at those table again, where we have Caesar looking at the system requirements and be able to, at the moment, it's a very laborious check about what the software requirement says and tracing it to the system requirement and making a hand-waving informal argument. Yeah, the software requirements actually do satisfy this system requirement, and we haven't missed any. So at the moment, this is where the manual review is needed. We hope that with the introduction of Caesar, some manual review will still be needed as sense checks are required, but it will alleviate some of the effort there. In which case, we'll have this, as my colleague Nick Tudor likes to call, the soup to nuts, a full course meal with FMA 7 and FMA 2 now addressed as well. Right, I think, yes, that's it. So open to questions here. I'll leave this presentation on screen and need to refer to it.
Okay, so we should thank you, Colin, in the usual way. We'll give you some reactions. Yeah, a bit of applause. And then open it up for questions. Yeah, I mean, Alice, you have your hand up.
Yeah.
Actually, I was trying to do a hand clap.
Oh. About the interface.
But I did have one question, but it was about one of your slides where you had all the different models that were being tested to see what the benefit of using the different approaches was. It was that one where you had the TA1 and TA2.
Oh yes.
Yes. So, yeah. And you were showing that two different people address the same problems and they got similar results. Would you have been? You'd have been pretty horrified if they didn't, wouldn't you?
Yeah. Well, I might not be showing it. no, I wouldn't be pointing it out and saying, "Look, that was like gold dust to us in terms of." Yeah. Yeah, that's again, it's not definitive; it's indicative, but it was a nice result to be able to show, as independent as you could practically do. They came with similar results. Mm-hmm. Mm-hmm. Indeed, that's the same true of yes. So what I said about the independent teams doing the blue, the green, so the Simulink design verifier, model works, and the conventional, they were separate teams who did not communicate, so there's independence. There wasn't any pollution in terms of, oh, we found these errors, so we know what to look for in this. That well, as far as we could guard against it, that didn't happen.
Mm-hmm. Yeah, great.
Andrew?
Okay, and then Andrew, yeah.
Hi, Colin. Thanks for the talk. I had the same problem as Alice. I can raise my hand, but I can't clap. But really appreciate the talk.
Thank you.
Going back to the Simulink stuff, you said that over time you have spotted error. Your tools have identified errors in the Simulink code generation.
So that's the clause. Yes.
So the clause work. So in the sort of conventional use of Simulink, there would be testing on the end, as you said.
Yeah,
it's probably hard for you to remember, but out of these small number of errors, were there any errors that you would think that might defeat something like MCDC testing, or was there any extra value that the proof was able to get into a corner that the systematic testing probably may not have?
Sorry, this is for my Siri. It's just interrupting me there. So I the answer to that is I don't think there would be. It's possible there'll be escapes from MCDC testing, but the point is you would get that right at the end, and that's a huge cost. So remember, this is all automatic towards the end. And the main place where errors did come up regularly was in terms of the design against the requirements. And sometimes it was because when you're doing design, as human beings, we find it easier to do how rather than what. We think operationally, if you like. And we find it harder to be abstract and talk about the what. So in the design, we'd identify what it should do, but hadn't done the corresponding what in the requirements. So that was a shortfall in the requirements, which came up in terms of the verification. And of course, similarly, there were slips that were done in the design, and it didn't quite do it. And that did happen quite a lot. And that kind of reflects experience, I think, empirical experience of the errors take place at the requirements and the design level. Generally, they don't, they're detected right at the end when you do testing. So eliminating those things earlier on saves time and cost. Eliminating them also saves, as I said, you get further benefits, the fact they haven't had escapes and you only catch them at the end. And then you got your residual possible errors, which are few and far between, to be honest. But you've still got a obligation to show the evidence that they are good enough, the code is acceptable. So there's the cost and time associated with that as well.
Sure, thanks. If I could have a quick follow-up question, Stuart.
Of course.
So related to requirements, I mean, you've made a really good sales pitch, because you're talking about real money savings. However, there's not many people do formal methods on requirements at that end of things. What is the biggest kind of roadblock you face convincing the people that hold the budgets in organizations to actually make that leap and invest a bit more early on?
Oh, so I don't think it's the people who hold the budgets. I think they see the business case, and they're all very keen on it. It's when you get towards the people who actually do it, have to do these sort of things, you get the resistance. Partly is there's automation in terms of code generation verification, so that does people out of a job, although we're exporting those sort of jobs anyway to India and China and so forth. And partly it's to do culture in terms of, I just want to get to code. Oh, you're holding me back. Why do I need to talk about, the capture says, you need to fill this part of the requirement in. Is there a time aspect you need to consider? So it's a kind of culture and irritation. Why do I have to do that? Then they do it, and then the penny drops. Oh, right, yes. Oh, right. They kind of get it. So there's initial resistance from the people who actually practice rather than the budget holders.
Okay, thanks.
Thanks, Andrew. Anybody else got any questions? I mean, I've got one, but I'll ask it if nobody else asks. Nobody. Okay, speak now or forever hold your peace, guys, because otherwise I'm going to ask a question. Okay, Andrew's put his hand down. A few years back, we worked on requirements for FADEX. Yeah.
Yeah.
That's full authority digital engine controllers on aircraft, and. Yeah. I wanted to ask you a question about requirements, because what we discovered was that when the code went on the box, there was a huge change in requirements. Yeah. When the box went on the engine, there was a huge change in requirements, maybe 20%. I mean, there were about somewhere between 4,000 and 5,000 requirements on the box. And then when the box and the engine went on the airframe, then again, there was another huge spike in requirements.
Yes.
And those huge spikes in requirement were massive costs, because of course the whole damn thing had to be re-engineered every time. So your smooth picture didn't really ring particularly true to me, actually, Colin.
But thank you for asking that question. That's another point. That's a really important point which I forgot to make, which is when we first presented these sort of tools to do automatic verification, people actually didn't see the value in the first pass through. It was in exactly these issues where you make changes to requirements and so forth. And the fact that you can run these, once you've done this, it's just deltas, and you can run through these things really rather quickly. And BA Systems Rochester, for example, who did the flight control for the Boeing 777 originally, that's where they saw the value in terms of the cost savings, because def taxis and requirements change are inevitable. So being able to support these through mechanical tools, be able to process them and just go through them, the things that don't change or change very little, and you can still show them. It's just the delta, the change of the size of the change is proportional to the cost. Now you actually are getting that sort of relationship. That's what we found. Yeah, and that is actually where more of the value lies, precisely because in aerospace and other places, you don't know what your requirements are, especially automotive. It's not until actually driving around, get the feel of the car, that's when they go, oh well, no, that's heavy steering or whatever.
I think one of the things was, if you look at the box onto the engine, then it was basically that there was a whole different engineering world, because the engine engineers used some kind of transfer function notation that didn't really fit very neatly with the more discrete world of the software engineer.
Absolutely. So that's a thing we're trying to bridge as well with the high level software requirements to the system requirements. Because at the moment, what you're relating to is they throw these things over the wall and they say, right, get on with it. We know what we mean. The software engineers doing their best to try and understand what they mean. These sort of requirements give you a way of pushing back on the system level. And indeed with CSER, we hope to be able to give them more pushback and saying, well, actually, I need to understand, I can't fill in this requirement unless I understand precisely what you mean. That there's always going to be aspects where there's going to be escapes, but what we're trying to do is to box them in more, and then when that you do have to do the engineering, minimize the cost of that in terms of verification.
Okay, Paul's got a question. Paul, I'll put my hand down now, Paul.
Yes, so I'm wondering about how tools affect the writing of requirements. So is there ever a danger that the limitations of what a tool can express in terms of requirements causes people to think about writing down some requirements but then leave out subtleties or other requirements that don't fit what the tool provides? And do you then have to kind of train the requirements writers to make sure they write down those things that are out with the tools separately anyway, so they're not forgotten?
So that's a good question, and I honestly can't say it wouldn't do that, have a consequence, which is partly why we're doing it through empirical development, as it were, trying it out with different customers, different sectors, and adjusting it. So we're learning from what they need to do. So there is an aspect of, I guess, I can't think of how this might actually play out, but it's not inconceivable that if you could design a language for requirements which precluded you thinking about certain important aspects, except it would bite you at some point.
But I'm thinking you actually gave an example with CSER, that the kind of pre-CSER, you can't talk about probability. So people might can write their specifications deterministically, whereas they actually might have they might be wanting to say a probability, express a probability, but they can't, so they don't. Rather than they don't screw it on a piece of paper and hand it over separately before they got CSER.
So, I don't think it would stop people thinking about those aspects. It's just that they wouldn't have the necessary direct support in order to do that, and the tool allows you to be able to bring those sort of record those sort of observations as well. So we're not constrained in terms of that, but that's a very good point.
Right. Okay, good. Thank you.
Okay, so we're at the top of the hour now, Colin. Yeah, we've I think we're out of time. Yeah, so this is just to say thank you very much again for a very interesting talk, and let's hope we get you back again to tell us precisely how everything's going with the full 7-course meal or whatever.
Yeah, the soup to nuts.
Great.
What course are we on now?
Yeah. Okay, great. Thank you very much.
No
Yeah.
problem. Thank you.
Bye now.
Bye, Colin.